In this pre-calculus lesson, we'll continue to explore the idea of approximating the integral with a bunch of rectangles here. And so I have one here. It actually looks like a square right here. But so if we have, let's see what it says. It says, find the approximate area beneath the curves. It says, so the first one is the upper limit is equal to 2 and the lower limit is equal to 0. So that means this would be our upper limit here, 2. And this will be our lower limit, 0, like this. And we're really trying to find the area beneath this curve, like here. So it's going to be between 0 and 2, up to the curve, and down along the curve, like that. So really all this area in here is the area we're going to try and find. And we're going to try and approximate it with a bunch of rectangles like we did in the previous lesson. So these are going to be our limits. Our upper limit is 2 and our lower limit is 0. And actually we really just call these the limits of integration. So if you recall, here's our integral sign like this. It reminds you of an S for the sum. And then we'll put our upper limit here and we'll put our lower limit here. And so this is going to be the integral of this equation, 0.5 x squared. And what we need to do is we need to take the integral of 0.5 x squared. So essentially what that means is this gets converted into another equation when you take the integral. And there's rules for taking an integral. And the rule for taking this particular type of equation is you take a look at that exponent 2 and you raise it by 1 to 3. And then you take the same 0.5x and you then divide it by this same number 3. So it really becomes 0.5 x cubed. See if I can squeeze that x in there. There it is, 0.5 x cubed. Did you get that? Let's barely see it. And all that divided by 3. So what I did, I just took the integral of this equation. Alright, I raised the exponent by 1, turned it into x cubed, and I divide by that number there. And so what I have down here is you take the integral. And that's what we did. We took the integral. And then the next thing you do is you're going to evaluate the integral. And you'll sometimes see it like this. They'll put a little straight line like that. And you'll put your same limits of integration up here. Here's your upper bounds and here's your lower bounds. Like that. And then you're going to evaluate it. And what you do is you take this value, the upper limit, and you plug it into the equation. So this would be, you plug 2 into x, and that would be 2 cubed is equal to 8. You multiply that times 0.5, that's equals to 4. And you divide it by 3. So by evaluating it, we get 4/3 for the upper limit. And then you have to do the same thing with the lower limit. You plug 0 into x, and 0 cubed is 0, so this lower limit becomes 0. And so you subtract the lower limit from the upper limit. And then the actual area is exactly 4/3. That area under the curve is exactly equal to 4/3. And so I'll show you that so you know down here this is exactly what you do. You plug in the upper limit and find the value, and you plug in the lower limit and find the value, and then you subtract the lower limit from the upper limit. Alright? So these are your limits of integration, the 2 and 0, and once you have, since you've given it a definite range in which to evaluate the integral like this between 0 and 2, you've essentially defined the limits of integration. You've defined the limits of integration, and that's what makes it a definite integral, because it's defined, okay, like that. If you did not have a limit of integration on top, you'll just see this integration sign all by itself, then that would be an indefinite integral, which means not defined. So well, we know exactly what this is equal to now, since we calculated the integral. So we essentially take the integral, creates this new equation, 0.5 x cubed over 3, and then we evaluate it between the limits of integration like that. So let's see what 4/3 is actually. 4 divided by 3 is equal to 1.33333 is the value in decimal format. But now let's go approximate it and see what the advantages are to approximating the integral. So we're going to define this as we'll just change the number of rectangles here. So in here, now it says the approximate integral is 2.5. Well, we know it's 1.333, but let's just add a bunch more rectangles. I'm up to 15, 27, 39, and you can see the approximate integral is getting down there. I'm up to 171, 235, 367, 451, 500 rectangles now I've done. And at 500 rectangles, we've approximated the area by taking each one of those itty bitty rectangles, calculating the area, and adding them all together. And then the approximate integral is 1.337336. So it's not quite there. We know the exact integral is 1.33333, like that. Well, but there was a little bit of work to do it the other way. You had to take the definite integral between 0 and 2, like that, and you had to and then you had to find the integral, right? There was your 0.5x squared, so there was that. And then you had to take the integral, which was equal to 0.5 x cubed divided by 3. And now since you took the integral, then you could evaluate the integral between 2 and 0, which were your limits of integration, your upper and lower limits, right there, 2 and 0, and that it was equal to 1.333, like this. So it's close, not quite there, but this was a quite simple equation to work with. This polynomial equation is pretty straightforward using an exponent like this. The rules for finding the integral, for taking the integral, are quite straightforward, but other equations are actually really, really difficult. I mean, really difficult. So, but when you're using the approximate approach, this is a numerical approach where we're finding the approximate integral, which maybe that's all I need. So maybe I'm designing a perfume bottle, and I want it to have the shape. Imagine you're looking straight down from above, and this is going to be the shape of the bottle, and then we'll extrude it into a height dimension. Well, since we know the area, we can extrude it into a height dimension and get the volume, and from there we can calculate the amount of, say, milliliters of perfume that would be in the bottle. Well, how exact do I need it to be? You know, do I need it to be 1.33, or would 1.337336 be okay? That actually might be okay. So with the computer, the power of the computer is that you have, just like this, you have virtually instant access to the approximate integral just by moving your limits of integration around like this. I'm just evaluating it at different points, or maybe I want to evaluate it between 0 and 3. Well, I did, and I instantly have the approximate integral just like that. All right, well, I hope that gives you an idea about calculating the areas underneath a curve and approximating the areas and the difference between them. All right, well, that's it for this lesson, and I'll see you in the next lesson.